Okay, hopefully everyone sees that. At the moment, since this is full screen, I'm unable to see any questions, but I will answer them at the end. All right, so I also have the time here, so I will try to be on time. So first of all, thank you for this invitation. Really, I appreciate that. And I think exploring neutrino is really fundamental. There are major questions in particle physics and in science. Now, history of neutrinos. Neutrinos started fairly low with just they didn't know what it was. Back in 1930, there was a paper as a desperate attempt to solve the really the unknown in beta decays that was observed. So something that violated the energy and momentum conservation. But then you can see there's been a huge increase in the number of papers, just to Nobel Prizes for Super K, for instance. So you can see that the experiments really started to get more knowledge, and the number of papers increased dramatically. But let's try to explore why are they are important. You will have during this conference several talks on neutrinos, so all of them will try to explore different parts, and they are all crucial. They are also fundamental. I'm just focusing on a particular part of that, but you can see that neutrinos can come from everywhere. So this is a plot, really, basically the probability of interaction cross-section, we call it, as a function of neutrino energy. So neutrinos are elementary particles, so they have some energy, and they can come from the Big Bang. They can come from our own Earth. They can come from the radioactive decays in our own Earth, and that's really quite interesting. They can come from the sun. They can come from atmospheric neutrinos, so basically cosmic rays. You have the proton decays with the atmosphere, and then you have neutrinos. And then they can come from other galactic or extragalactic sources, so to say something more about that. But they can also be human-made. They can come from reactor neutrinos, from reactors, from the fusion and really from the fission reactions. You have the neutrinos in the final state. They can come from the supernova neutrinos, other sources. So, and they really expand about wide range. So this was a big introduction, but because we want to delve into something more specific now, so we will discuss first what do we know about neutrinos. So we know a bit. We don't know so much. So we still have open questions. So we know they are part of the standard model, where standard model of particle physics is really the model, the standard indeed that is currently used in particle physics. Of course, what we are trying to do is whether there is anything beyond that. So they are part of that. They are fermions. They are already, though, indicating that we go beyond the standard model. Why? Because they do have a small mass. Whilst in the original formulation of the standard model back in the 60s, it was postulated there were particles without any mass, so zero mass. But what was observed was that they do have a mass. Why they do have a mass? Because it was observed that they oscillate. So it's a quantum mechanical process, and you can see that they oscillate between one quantum state and the other one through a mixing matrix, where this is a so this is a relation that relates the flavor eigenstates of the neutrinos. That is basically what we see, because this is what interacts with the matter, and the mass eigenstates, so the ones that are definite mass, they are the eigenvalues of the mass, and through a mixing matrix. And this is the so-called Pontecorvo-Naki-Sakakawa matrix. clearly called just a P-MNS matrix, and these are the corresponding matrix elements. But they are very important because they basically tells you how the neutrinos oscillate and what we can observe at the end. So that's a fundamental question. You can, this is a 3x3 matrix. And then you can divide that, into three products of three rotational matrices. So we can matrix 1, matrix 2, matrix 3, and the elements that appear here, they are specific elements, meaning that this is a unitary matrix 3x3. So just because of just because it's a unitary matrix and 3x3, we know that the number of parameters, free parameters, are 3 real parameters and 1 complex phase. Now, these 3 real parameters, we call them rotational angles. We could have called it in another way, but this is just a convention. So we call them rotation angles, and we have a complex phase. It's again a convention. We call them theta 1, 2, theta 2, 3, theta 1, 3. And the complex phase is the CP violation phase, which we are going to discuss in a moment. So the 3 complex phases are basically related to different types of oscillations. Why I must say that? Because you can see here that we have split this equation as a product of three matrices. And this one, the first one, is mainly associated to the oscillation of neutrinos coming from the sun. And these are electron neutrinos. They have a specific energy, which is not too high. And this other one instead is really a fairly different spectrum. That has atmospheric neutrinos. They are fairly energetic. They come from the atmosphere down on Earth. And then in the middle, they are so-called accelerator neutrino experiments or angles. So we can split them into that. And then what we are going to do, as I mentioned, we have an oscillation between the different states, flavor states. So we can look at what happens once we start with a particular state and we arrive at, and after a bit we measure what we have in this beam. So we start with a beam, so a composite number of particular neutrinos, and then we observe at a certain distance what happens to those ones. And this is due to the oscillation due to the matrix. So what happens is that you relate one state to the other one, what you have at the beginning to what you have at the end, and the equation, the oscillation equation depends on the these mixing matrices. So depends on these parameters. Now this is a specific equation because this is assumes just that it's a 2x2 matrix. And why is it that? Because it's the easiest one I can write. But to highlight that there is a dependence of when you have the neutrinos generated to when you observe those ones. That's the major thing. And this dependence is on the distance, the energy of the neutrinos, and then the delta m square, because as I mentioned, they do have a mass, or better, we observe the oscillations, so we said that they have a mass. And this is the difference in mass squares. And this is the much more complicated equation. This is for 3x3. They have different components. They depend on the interaction in the matter, because matter is composed of electrons. So if you have specific neutrino electrons, they interact with the corresponding electrons in the atoms. And then we have this is the most important part for us, the Dcp violation. So you do have a term that depends on this delta Cp, and this is a term that is different for neutrinos and antineutrinos. So basically, measuring the oscillations for neutrinos and antineutrinos, we'll be able to observe this term here, because the equations will be different. And so there are a couple of things that are important here. So delta CPM, I said, compares neutrinos to antineutrinos. So we can measure this one. We can also measure, once we have the neutrinos and antineutrinos, another thing, that is these oscillation probabilities I mentioned, so whether they disappear. So you can see that this is basically this equation that you write as a function of the energy. You can see that after a bit they disappear, then they appear, they disappear, and disappear, and appear again. So you have this oscillating process, and then we can measure these ones. So bottom line is that we do have neutrinos, we know what they are, we want to measure what appears, and from what it appears, we'll be able to measure parameters related to the mixing matrix, and in particular, we'll be able to measure delta Cp. There is another parameter that is missing. We'll not discuss this too much, but I think it's a crucial parameter. And this is the so-called delta M square parameter, because this is the difference between the mass squares of the neutrinos, 1, 2, or 3. And we don't know whether the ordering of the masses is M1 is the minimum mass, M2 is the middle, and M3 is the largest, or there is a mixing M3, M1, M2. How can we determine that? Just having the neutrinos going through enough part of the Earth or enough something matter, because in that way we'll be able to distinguish the different components. This happened in the sun because if you remember, I mentioned there are neutrinos coming from the sun. In that case, you pass through all the sun. There's lots of matter there, and you will be able to then measure them on Earth and distinguish whether they are one or the other one. For that particular 1-2 case, but you are not able to do that on Earth yet. So this is an open question, whether we have this configuration or this other configuration. And we call them basically one norm hierarchy, and this other one inverted hierarchy. So how much do we know? We know, and we know these three angles. We don't know them all with the same precision, and but there are open questions still, and these are particular plots that compare. They are two-dimensional plots. We will see several of these two-dimensional plots that compare either delta Cp or one of the mixing parameters with another parameters. They're usually in signs, so you can see that there is a limited range. And so what happens is that in this probability equation, there is always a dependence on one parameter to the other one. So we are also looking at usually at two, but often the fit is done with more parameters to determine those ones. And the dot that you can see there is the minimum. So for instance, here you can see, well, okay, this is the minimum for this angle, and this is the minimum from this other angle. But what I want to say is just that we do have these parameters, but there are still some unknown questions. We still don't know the value actually of delta Cp. That's the main question we want to address. We still don't know in some cases which one of the two ranges it is, higher than 45, less than 45 degrees. So there are still open questions, and then they change really the configuration of how the neutrinos behave. So it's important to address and try to understand what it means. So basically, pending issues is that this angle, we don't know whether it's more or less of 45 degrees. So what we call maximum value of theta 2-3. So we don't know, and that depends really the percentage of a type of neutrinos with respect to the other one. We don't know the mass ordering I just mentioned, and we don't know the Cp phase. But of all of that, we just focus really mainly on this one. And here is just a list of the parameters. If you go into neutrino physics. If you have any curiosity, you can look at what happens having fitted all the results that come from the different experiments. And you can see that the results are always presented in a double form, norm and inverted ordering, because they do have this value delta m squared that is different, just the sign, but they indicate a different ordering. So often when you see the results of neutrinos that do have this different mention of the different results, because the theory behind that is a little bit different. And so then, yeah, you can see we did measure, but we didn't measure them well enough. And on top of that, CP violation needs to be fully measured. So let's move on then to really a major, or if not the most important, well, my preference, at least, the topic on neutrino physics, that is the matter-antimatter asymmetry. So the underlying assumption clearly is that the universe is matter-dominated. This is matter. I'm matter. Everything is matter. So it's clearly matter-dominated. But this has been measured not just because we see that, but there is evidence also from several other sources that also in the universe there is this dominance of matter with respect to antimatter. So the modern perspective really is that there is an excess of matter, or if there is some antimatter, it's in some pockets we are not able to see. So why are we in this condition? How it may have happened? So the modern perspective is really there is a process from the origin of the universe, from the Big Bang, that provided the current universe that is full of matter. And this is called baryogenesis. So really the creation really of baryons instead of antibaryons. So matter with respect to antimatter. And baryons is really the hadronic, so the quark part of the list of elementary particles we have. So how did we create more of those ones? So 3 conditions were postulated by Sakharov a few decades ago, and he's mentioned, and is currently accepted, that the conditions in order to have this baryogenesis is that there must be a process that violates baryon, the baryon number. So what do we mean? When you have an elementary process that you start from one reaction and you arrive to the other one, there are, if you remember from your courses, or possibly if you remember from your courses, depending what you took, there is a parameter that it must be constant. That is the baryon number. So basically, it's telling you the type of a baryon, or this is a composition of quarks, is the same in the initial and final state. So this number associated to this kind of particles. So this is one condition. He says, well, okay, no, this needs to be violated. You can't have this kind of process anymore. Another condition is that you can have a Cncp violation. So charge and the charge parity violation. So basically changing the particles into antiparticles. And then out of equilibrium, that's the condition, and that happen out of equilibrium. But what we want to address is mainly Cncp violation, and then the baryon number. I'll mention that. But in particular, nowadays, we are more than looking at baryon number generation, elliptogenesis, because elliptogenesis is a mechanism, is a model developed by theorists to move from an asymmetry in the number of leptons to an asymmetry in the number of baryons. So first let's say, well, okay, we need to have a baryon asymmetry. No, we first need to have a leptogenesis asymmetry, and then we go into the baryon asymmetry. So then there are a couple of things I want to bring forward before we move on to some more experimental results. So all the models that we are going to look at, they employ or in general, if you have a models employing CP and CPT violation to explain the matter-antimatter symmetry, they require B violation, as we said. But in the standard model, really, it's not really B that is conserved. It's the difference B minus L. So this is well conserved in the standard model. So we can look for B violation, but at the same time, we can look also for L violation. So we can continue looking in B, but it's really, we could look in lepton violation. And why is it important for us? Because these addresses neutrinos. We can have neutrinos that violate the lepton number. And this is the second part towards the end that we'll discuss. So now we are starting to establish the criteria. So we want to have a baryon. We can look for that, but also lepton, or it could be lepton violation. And then the other one is the Dcp violation. The leptogenesis is a kind of model that mixes all together all this information. And why CISO? As you can see here, CISO is really a CISO. So meaning that it assumes that you have the normal neutrinos that are fairly low mass. So they were so low their masses that in the beginning they thought they didn't have any mass. But now we can introduce a right-handed neutrinos, so another type of neutrinos that are very high mass. So now we have these two types of neutrinos, and the mass is different. Basically, they are inversely proportional. This is why it's really called the CISO mechanism. They, in this model, these types of neutrinos were introduced, and this model manages to predict basically the leptogenesis, so the fact that there is an imbalance in the number, there are processes that generate an increase in the number of leptons with respect to antileptons, so matter with respect to antimatter, and then there is a process that then generates the corresponding baryon asymmetry. So these models are quite popular, and there are different types. But once we get CP violation, we can look at these ones and see whether it makes sense. And sorry, I go back then just quickly to the lepton violation we were mentioning. The lepton violation is what we'll discuss later. That means whether neutrinos are Majoran or Dirac. If they are Majoran, they have a lepton number violation. That is what we are looking at. And Majorana condition means that the particles are identical to their own antiparticles. So neutrinos are the same as antineutrinos, which is different from what we have in normal matter, that is the Dirac particles. So now we are looking at the two things in order, CP violation and then lepton violation. More in general, these are the questions we are going to focus on. So CP violation, and also, since we are looking at neutrinos, since we have a plethora of neutrinos, then we can also address the other open questions that are the mixing angles. So as I mentioned, there are still questions like, is this larger or smaller than 45 degrees? What is the exact value? So we can look at those ones as well with the same basically tools. So experiments are expensive, so we just use that for everything. But then there are other open questions that we are not going to address now. In some cases, you may see them later in other talks. So what's the absolute value of neutrino masses is? So if we assume that they are Dirac neutrinos, what's their mass really? That's an open question. We know that it's very low, but we don't have any measurement of the neutrino mass. Mass ordering as well, although it may come partially through what I'm going to show, although we don't have an answer yet there. Then the nature of neutrinos, Dirac Majoran, is what we actually will mention. But on top of that, are there any sterile neutrinos? What does it mean, sterile neutrinos? Neutrinos that don't interact with the normal matter. So it's a little bit difficult to observe those ones, but there are many studies to try to understand whether they exist. So we have an exciting program for neutrino physics, and now we're just focusing on some specific questions. So what we are going to look at now is first introduce long baseline neutrino experiments, and then just highlight the results. So first we need to understand what they are, the so-called long baseline neutrino experiments. Long baseline means that, as I mentioned before, you have a starting point when you have a neutrino and an end line when you want to measure those ones. So then we call long baseline a neutrino experiment. You have an initial point when you produce the neutrinos. These are human-made, and the final point when you measure them. How they can be produced? They can be produced through accelerators. Of course, they don't have a charge, so you don't produce neutrinos. You produce protons. They interact with some target, then they produce pions, and then muons, and finally from their decay we have muon neutrinos. So how it happens, you can produce neutrinos, you can produce just charged particles, and then from the decay of these charged particles, namely muons, you do have the neutrinos in the final state, and that corresponds to your beam. So beam is a beam of neutrinos, and then you have them produced in one part of the from where your origin of your accelerator is, and then determined their property at a certain distance. There are some tricks that are very smart from the experimental point of view. You may slightly tilt your fire detector. And why can you do that? Because you can see that due to the kinematics of this decay, you do have the neutrinos that are seen more focused. So what does it mean focus with the smaller energy resolution? So, and these are quite interesting because this means you can say more precisely what the energy is. But these ones have much larger statistics, so there are both counts really, experiments with at a tilted angle and experiments that actually are here, not at the tilted angle. So they are straight here, and these ones will see the full distribution. And there are two major accelerators producing neutrinos nowadays. And those are one in the US that is called Fermilab, and one is in Japan. So this is a little bit small, but this is close to Chicago, this Fermilab laboratory. And there are several accelerators, really, it's many. They are being upgraded, etc. So you can see that they produce both the neutrinos that they have a tilted angle, and neutrinos that go straight, and they have different advantages, and they have different experiments. So it's a very complex experiment. We'll just address two in the next results. So the so-called NOVA and the upgrade that is June. But again, what you need to have, since you need to accelerate the charge of the particles, you need to have a powerful accelerators that accelerate the protons really, and then from the interaction of the protons with the target, you will have then eventually the neutrinos coming from the decays of the muon. So this is why these are very important, and they have many experiments running NOVA and in the future June. The other one is on the other side of the universe, the Earth, that is in Japan. So you have again a big accelerator, and then you can see those neutrinos about 300 meters away here on the other side of Japan, closer to Korea. And now I will focus very briefly. I just want to show some results, because clearly looking at the experimental details is fairly complex, but we want to show the basic concepts of what's happening. So in this case, you do have the original generation of neutrinos. You have what we call near detector. So you generate those ones, but that's an accelerator. You don't know exactly what you have. You need to have a detector that determines those ones. And that is called a near detector. And then at a certain distance, in this case, 100 meters away, in the US, it's much bigger, thousands of meters away, so thousands of kilometers. You do have a far detector where you determine the neutrinos after the oscillations. So, and this is what happens. This is basically the integrated, it's the corresponding luminosity. It's just a different name called here, number of protons on target. It's just accumulation of neutrinos from the origin, actually, these experiments, 2010 up to now. So you just see that there is an integrated luminosity of protons on target that increases. And this is the plot you can see at the far detector. So you can see that there is a decrease. This is the probability equation basically as a function of the neutrino energy. And due to you start with the type muon, but we said you go from a probability of having one neutrino to another one. So these changes, you need to have a decrease here because you have something that appears that we'll see in the next slides, really. So this one decreases, becomes mainly a neutrino electron, and you can see the dip. And that's really exciting, is what you can see from the probability equation. So yes, this is what we see. We have the evidence that there are neutrino oscillations, and we see the dip. And this is the probability really of oscillation, the probability that has oscillated, that has disappeared at the far detector. So the near detector you have a peak, at the far detector you have this one for neutrinos and antineutrinos. And this is just the two-dimensional plot. So these are confidence levels. This confidence level in the funnest of events you have observed in the funnest state, and then you can measure, determine the parameters theta to 3 and delta m square. And this is once you combine all of them together from the different experiments. So you're able to determine, basically, you can see here a value of a sine square theta to 3 and delta m square, but the experiments are not all the same. So you can see that we still have a little bit of work to do to try to understand the exact value, but things are improving, and it's really very exciting to see this dip. The interesting bit for CP, though, is the appearance. So once you measure you saw a dip, so they disappeared. Now you look at the appearance, and you see the electrons, neutrino electrons. And that is the difference between neutrino electrons and antineutrino electrons that gives you CP. And then this is really the flux. So what you would see, the fine detector of neutrinos and antineutrinos. And different, depending on the value of delta CP, that could be different. So measuring the far detector neutrinos, electron neutrinos, or electron antineutrinos, that will give you the corresponding value of delta CP. That is the Dcp violating phase. And then this is what you observe, but then you can interpret that, okay, these are my experimental results, this is the flux, then I want to look at the parameters, and then this is what you can see here, this delta Cp. So that's the difference between the neutrinos and antineutrinos as a function of delta Cp. And then you should see, these are just theoretical curve. So you should see the dot that appears, your data that will appear somewhere. So yeah, so now we are focusing on neutrinos, electron neutrinos. First of all, you see them. You see the electron neutrinos. You see that they appear, and also antineutrinos. You see that they are there. But you can see already here by eyes that they are different. There isn't really the same number of neutrinos and antineutrinos. yeah, so they, yeah, for this you will need also corresponding beam, but I just focus that with the same normalization, we do see a difference between neutrinos and antineutrinos appearing in the fire detector. And then again, we can interpret that. What does it mean? In this case, it means that we do some statistical analysis that would require a lecture per se. But in this case, we just want to, in this talk, we just want to look at that this result has implications, because we see that the favored result appears at the specific value of delta Cp. And this is the maximum. It could have appeared somewhere here, but this is it's the maximum. So it's a maximum violation of delta Cp. This is still at the level of 3 sigma, really. So it's not really an observation. So we really need to understand this one and have the observation at 5 sigma to be 100% sure that actually we have a Cp violation, and what are the implications, what are the values. And here is just more, basically more information regarding these values that have been observed. So the region of exclusion. So basically, again, the value that we have been seeing for delta Cp. There are many other constraints that we can put on the values of the other parameters, but we really, in this case, we just want to focus on one. I just mentioned other constraints, like, for instance, the sector with the 1-3 angles, because here you can see that this is reactor constraints, because that is measured from another detector, not from, well, also from the long baselines, but we used the most precise measurements from reactor experiments. But anyway, here we got Cp, delta Cp, or at least we got our best estimate so far of delta Cp. But it's not enough. We got 1 point. We need to really span the full range, and we need to understand, really to observe that. So arrive to 5 sigma. But that's not easy. It's not like you run forever. You can run forever, but then it's going to take 100 years. You need to run for a specific, with boost upping basically your detector. So you need to increase the energy. You need to increase, sorry, the luminosity, the protons on target, to improve the detectors. And there is then a big campaign to try to improve the detector. This is just for the near detector, and in a little bit I'll mention the far detector. In the US, I'll be very brief on this one. In the US, you have a similar experiment that is called NOVA, but the characteristics that distinguish that very much are that the distance between the initial and the far detector are much more. So here we are talking about of the order of 1,000 kilometers. In the other case, also 300 kilometers. So the probability equation is different. And similarly, the experiments are very different. So this is on the surface, so it has a lot of cosmics, you can guess, and so it's very difficult to understand what's there, but they are extremely good with all these artificial intelligence technologies. So you will be able to determine what you can see there, and again, you be able to determine what you can interpret. So, and then you can get the similar results like you got before. Are they similar? That's the question. So T2K and NOVA do measure the same quantities. There are some differences between the two experiments, and then the moment they are being addressed, that could be just at the level of what the assumptions are when you interpret the results, but they show some differences that at the moment the two experiments are trying to address. This is really, so you can see that one goes in one direction, and the other one is more, this is T2K, that is, no, sorry, minus, but T2K is more over around the value. So there are some differences that the experiments I try to address. So as I mentioned before, for T2K, there is a program to go beyond that, that is creating with a more powerful experiment. And similarly for NOVA, up to 2025, there is an increase of the luminosity. So that will allow to determine more parameters, especially what I didn't mention too much, that is the difference between, the normal and inverted hierarchy that you can determine, because there is quite a lot of Earth that is crossed by neutrinos. One thing that I like just to mention is that when neutrinos interact with the matter, their cross-section, so probability of interaction, is a little bit a complex issue, because they interact with the nucleus, and there are several nucleons. So you can't really say, okay, I interact with a proton, with a neutron. You need to make assumptions, and there are modeling, and those modeling need to be tested. There aren't enough measurements. So there is a campaign of trying to address also what happens when you do try to look at specific interactions of the neutrinos with specific detectors, with the specific targets. So you have your far detector, you interact with this one, but the probability of interaction is something that depends on it's the cross-section. So you need to have a precise value of the cross-section in order to determine delta CP. Do you have it? There's still quite a lot of investigation in that. So it's neutrino physics is not as easy as one might think. Well, you have a neutrino, it's very clean, because there are just weak interactions. And no, it's more complex, because you have a nucleus, and the nucleus means protons and neutrons together, linked by the strong force. So you need to imply that you have a strong force modeling as well. So it's a bit more complex, and this is why there are still some errors, uncertainties that depend on the modeling. And here you can see, just to give you an example, you can see that the modeling and the experimental results are not necessarily the same, and you need to address those ones in order to go down and in your uncertainty. So this is, I think, the most crucial bit when you have neutrinos, that you need to try to understand the probability of neutrino interaction with the detector. And yes, a joint effort is needed. So this is just what everyone wants to do. And it's not just the big detectors, but even trying to understand these nuclear interactions that are crucial. Now I will briefly mention to highlight the complexity of the big future experiments that we run after 2025, around 2027. And one is Dune. And what's there? You have a long baseline, because this is in the US. So you start from Fermilab. You have a far detector 1,300 kilometers away. And these are giant experiments. You need to start now to run. The technology is very complex. It's called liquid argon, and it needs quite a lot of work that needs to be done. And here, just to indicate the complexity of these experiments, you do have a flux that you produce, but then you need to detect those ones. So you need to detect at the very beginning, as I said, you have a near detector, then you need to measure what you get from the near detector, and then you need to look at the far detector. So it's quite a cumbersome process. And at the end, what do you need to do? You need to measure CP violation and other parameters. And this shows just the basically the sensitivity to CP violation as a function of the years. So you measure something with the previous experiments, 3 sigma at most, but then you need to span the full range and measure the full value. at 5 sigma. So you can see that this is really the precision, the sensitivity as a function of the years. If any one of you is interested, the corresponding prototyping of this big experiment is actually at CERN, so it's not not really at the moment at Fermilab, but it's at CERN, because CERN, you know, it's a huge lab and there's huge facilities. So here you can see that in this area at CERN there is now currently ongoing work for this June experiment. That will be again in Japan. We have the famous Upper Kamiokande experiment, as mentioned. Sorry, famous. I think it's famous, but you possibly know more Super Kamiokande that was used for the determination of the atmospheric neutrinos oscillations. And these, it's the same baseline as T2K, so about 300 kilometers, but it's much larger detector, almost 10 times larger at the far detector, and then you have an initial beam that is with the same accelerator but more powerful. And even in this case, there are sensitivity studies that basically within 3 years, 3-5 years, with these nominal sensitivities and improve the near detector, you should be able to determine CP violation. And the precision really depends on how much beam power we manage to get the detector in the final state. I will just mention that it's not just the beam that are important. The beam are important as well as the atmospherics. So the atmospheric neutrinos that comes from the interaction of the protons with the atmosphere, then you have the decays into pions with neutrinos, and then muon with neutrinos, and then you will see them on Earth. You see the neutrinos. They are still important value that can be used together with the beam in order to look at oscillations, and they were actually the first evidence of oscillations, because you can measure basically from the bottom and top of Earth, so different path lengths. And that can as well help to determine CP as well as to address the matter, the mass ordering. Before we move on to lepton violation, fairly briefly, I just want to highlight that in these experiments, given the large, huge detector in the final state, you can also measure proton decays. So proton decays are protons coming from that can decay. So you have a Dcp violation. Remember violation. So we need to look at proton decays. Have we observed those ones? Not yet. But we need to have lots of nucleons, so large detectors, in order to have some chance to observe those ones. And this is a future. A part of the future plan for ABK. In the last couple of slides, really, I like to mention the neutrinoless double beta decay. So we said neutrinos, the standard particles are Dirac particles, but neutrinos have been postulated could be Majorana particles. What does it mean? It means that neutrinos are the same as antineutrinos. And what does it mean? It means that when you look at these diagrams, and instead of having neutrinos and antineutrinos, you do have the same line. So you don't have a distinction between the two. Experimentally, then we can observe that the two neutrinos are the same, or they are not the same. This indicates the lepton number violation indeed, because in the final state you will see that there is a violation really of the lepton number, because you will not observe these neutrinos. So neutrinoless double beta decays, sorry, neutrinoless because indeed you don't observe the neutrinos in the final state, are the possible evidence of Majorana neutrinos and lepton violation. And how do you do that? You need to look at nuclei that undergo double beta decays. So they undergo one beta decay after the other, and this is, say, the nuclides, the visual plot for the nuclides. In this case, when you look at the final state electrons, you will see this peak here. Instead of observing something that is very smooth, you will observe this one, the double beta decay peak. And there are several nuclei that can undergo the double beta decays. So what we want to look at is the specific phenomena, the neutrino, but in this case without the neutrinos. So instead of having a sort of instead of having the in this case, what we will observe is really the two neutrinos. So we'll observe the peak in the final distribution. So this is again has its own matrix and its own additional somehow terminology. So we introduce in this matrix element, we will introduce double beta decay mass, as well as we have a nuclear mass matrix. So this introduces a different set of variables and a different set of uncertainties, really, because we need to know from the nuclear theory of what the value of this nuclear mass matrix is. So nuclear physics is extremely fundamental. And here you can see just a very a complex really plot, but shows the uncertainties you have on this mixing matrix. So this is still fully very much underway and under study. So what we want to determine to minimize is the error on this matrix in order to see whether really we can interpret our result as due to the mixing to lepton violation. And again, the parameter m versus the mass shows that we can measure this parameter. We can what we do actually. This is just the interpretation. Like before, you were looking at those two-dimensional contours, and now you can look in a different way at this maxis, but it's just an interpretation of what actually you do observe from the experimental point of view. Before, you were observing these number of neutrino electron or antineutrino electrons. Now you're observing electrons in the final state. So you just need to interpret the spectrum you have and try to see whether it does make sense, whether you are really observing these neutrinoless double beta decay. And at the moment, not yet. So it's still a wide field of search. The other part, just before I very much conclude, that I want to highlight is that these they depend in order to minimize, in order to reduce the uncertainty on the final results. What we want to do is to maximize the number of isotopes and also the time and the background to minimize. So there are, of course, conditions that you need to try to achieve in order to obtain your violation or to measure the lepton violation. How do you can achieve that? There are many experiments. So this time I'm not going to focus to one. I just say there are different technologies that can address the either the big size or the maximize the exposure or minimize the background. So you can use different techniques, and indeed you can see a very wide panorama, landscape of many experiments. So before you had two, or one in Japan, one in the US. Now you have many more. They're all different, they're all relevant, and they are not necessarily so different in some cases. They are just the evolution from one to the other one. This is their sensitivity versus versus the exposure, so basically the time. So these are the future and this is the present. So you can see that now it's much more complex. Can they be the same? They have different technologies, so it's a little bit complex. Okay, now we are concluding. So we have a variety of experiments. We have a variety of detectors we are looking at. We are involved at King's in this bit here, and we are involved as well in Snow Plus. But that means that there are important questions that we want to address, and actually crucial questions like matter-antimatter symmetry that we want to address in different ways in the next few years, and on which we are working on. So finally, there's been a steady increase in neutrinos in the last years, in the interest in neutrinos in the last decades, really. And then there is an intense program worldwide in which we are giving very important contributions, I hope. And then for the current experiments, we culminate as well towards the end of this decade with more work that has been done. Okay, that's all for now. Thank you.